For the introduction, my name is Kangwook. I'm a postdoc at KAIST. This is a joint work with Ji-chan and Chang-ho at KAIST. I'm going to talk about large-scale and interpretable collaborative filtering method for educational data. So let me just briefly explain what is the problem that we are looking at. So if you try to define what learning analytics means, so it consists of three phases. First, you have to collect data. It can come from MOOCs or it can come from mobile apps. It might come from traditional standardized exams. And then you want to do some data analysis. And then later you want to do something like prediction, recommendation, personalization, or you want to design new educational content based on the user. So in today's talk, we are going to focus on a method to apply machine learning algorithms to do the data analysis. And then the goal is to predict students' responses to the questions that they have. It's not shown to the students yet. Okay, so it consists of two phases. In the training phase, we collect students' history on the previous exams, and we run the learning algorithm and obtain these student features and question features. And then in the inference phase, we try to predict whether the student is going to get it correct or no for the problems that they have not seen yet. So for instance, in this example, we have a new student coming into the system, and he reports the scores for the first 30 problems. And then we run the algorithm and then try to predict how he's going to do for the rest of the problem, let's say problem 31 to the end. So the traditional method to tackle this problem is you first define some response model and run some algorithm to predict the latent features. So this is a method that is proposed by Bergner et al. In 2012 and also Lan et al. In 2014. So let me just briefly recap what the high-level idea is. We first define the student and question features. So let's say if we have n users, you define an n by r vector matrix, and the r is the number of hidden concepts. So each row of L represents the latent feature of the student, and you stack them and define the L, which is the student feature matrix. And you can also define a similar feature matrix for questions. So there are m questions, and each question also is associated with a length r vector. You stack them and you define r. If you multiply n and r, then you define it as x, and you call it that level of understanding. And then you apply some element-wise non-decreasing function, say phi here, let's say without loss of gender, you can assume it's logistic. And then you can view it as a probability of correct guess. And then the observations we are making is a random realizations of the ordinary random variables where the parameter is associated with each of the key elements. Okay. The goal is to design an algorithm that observes this y, which are correct or incorrect responses, and try to estimate what the underlying L and R features. There are a few concerns with the existing algorithms following this approach. The first concern is scalability. So the reason why we have to really care about the scalability in this, especially in this domain, is if you think about the movie recommendation, people are not watching movie 10 times a day or 100 times a day. But if you look at the educational system, some crazy students work on the, I don't know, more than hundreds of problems per day, or sometimes thousands of problems a day. So the number of responses that you have to deal with is growing much faster than the existing areas like movie recommendations, and also much faster than the e-commerce areas. So you really have to care about scalability because the number of responses you have to deal with is much large and also growing much faster. But the problem with the existing algorithms are that most of the algorithms have superlinear time or memory complexity. For instance, if you think about the n as the number of users, m as the number of questions, then the time and memory complexities are mostly higher or equal to order of n times n. Okay, I'm going to skip those details, but that's how the existing algorithms are. And also they are barely parallelizable or distributable. Okay? So if you think about the case where in 10 years we have like billions of responses from the students, you cannot deal with it with a one machine or one processor, then you have to parallelize it or you have to distribute it. The problem is the existing algorithms are not amenable for those kinds of approaches. So that's one thing that we found from the previous approaches. The second issue is the interpretability. It's also different from the e-commerce, or actually, I'm not sure about the e-commerce, but different from, let's say, movie recommendation. You do not actually care about why this guy is really into this movie and why this guy is really hating this movie. We don't care about the underlying behavior because the ultimate goal is to just predict whether this guy is going to like this movie or not. But in this education area, you really have to understand why this guy is getting this problem correct and why this guy is getting this problem incorrect. Because that's the way we want to understand the student, and we have to design new educational content. So interpretability is the key thing that you have to really care about in this domain. Sorry. Sorry about it. And if you look at the literature, there are a few exceptions that have designed specifically for higher interpretability, but most of the works do not provide good interpretability in general. There are a few exceptions, and you can take a look at the paper for more details. So let me briefly explain what I mean by the existing algorithm have lower interpretability. So if you think about the response model that I described, and let's say you just run an existing algorithm, then you'll get something like this. So consider that for some user I and question j, you get this kind of latent vector. So for user I, you get this li, 0, 2, 3, 1.5, 0.5. For question j, you get this r vector. If you try to interpret what these numbers mean, then you may think something like this. Okay, so the numbers in r vector are positive except for one guy. So what does that mean? It means that some people might think that this is the concept that you must not know, because if you know this concept, then that it will be that implies that your value corresponding to the li will be higher, and it decreases the value of x and decreases the probability of getting this problem correct. So it kind of gives you some crazy interpretation. Actually, this is also not consistent because if you think about it, so you can also flip the signs of the any column within the L's and R's and maintain the same values for x, which means that these are equivalently likely, they are equally likely weighted features, or in other words, there are many globally optimal solutions in terms of likelihood. So you might end up getting with this kind of latent features, or you might be ending up getting this kind of features. So if you try to interpret this kind of vectors, then you do not get anything useful or anything consistent. Okay? So one simple fix is to just make them L and R non-negative. Just add this L and R non-negative constraint and try to solve some optimization problem. But the problem is it's still there. So if you look at this example now L and R are now R positive or non-negative, and you can see that everything is accumulative now. So basically, what I mean by accumulative is you basically multiply the first element of L and R and add it to the second product and so on, then you get the x. So maybe you might interpret the vector R by looking at the first element, and hey, this is the element that has the highest value. So maybe the first hidden concept is the most important concept for question J, or solving question J. Is that correct? So you might think so, but the problem is this is also still not consistent, because if you scale down, let's say, force coordinate of the force element of L and scale up the force element of R, then you still remain all the values of X and still remaining all the values of P, so you still get the same likelihood. It means that so if you try to interpret this result, then you get a different interpretation. Seems like your force concept is the most important one. If you end up with getting the solution, but for the first case, you were seeing the first one as the most important one. Okay. So in order to solve this problem as well, it's a very simple fix. You have to confine all the elements of L and R to, let's say, a 0, 1 range, then you're done. Okay. It's a very simple fix. There's a little bit more details about the fix, but I can skip the details. So let's talk about the algorithm for the new model. So very simple. So you have to write down the ML optimization. So you write down the likelihood here, and then add the low rank regularizer here, and then these are the all new constraints that we introduced here. Okay. So these are the details, but in the end, basically, for scalability, we want to use some stochastic gradient type, different type of algorithm. So you can just apply the product to the 3D and obtain this algorithm. So let me briefly talk about the time complexity and memory complexity. So time complexity is optimal because it's linear in the number of data points. It does not depend on the number of users or number of questions. So you can deal with any number of users, any number of questions. You can also see that memory complexity is also optimal because it's the sum of the number of data points, which is that you always have to pay for. And also the first term is the R times n plus m. So you do not depend on the square of the n and n, or you only depend on linear in n and linear in n. And also it's inherently parallelizable because FGD itself is very easy to parallelize. And also especially for the matrix factorization problem, there's a known method that can be used to parallelize this for multiple cores in a better way. You can take a look at the paper done by Van Wert and Chris Rea in 2013. Okay, so let me now describe the experimental result. So for the data set, we are looking at actually, we did collaboration with a Korean startup. So that's the reason why we looked at this specific data set. So I don't know whether you're familiar with TOEIC. It's a standardized exam, English exam in Korea, which is the most popular in Korea. People have to take it just to apply to universities or colleges or companies. It consists of 150 multiple choice questions. It has 7 different parts, reading and listening. In this experiment, we focus on part 5 and part 6. Basically, those parts are for filling the blank. For part 5, you are given a single sentence. You have to fill the single word. For part 6, you are given a single paragraph, and you have to fill the blank. So we collected 4,200 TOEIC questions, and we launched an app in Korea. We collected data from the last year, actually, basically from 2016 January to this year's January. Surprisingly, many students have signed up. More than 120K students signed up. And we've collected 9 million responses. Turns out there are many outliers because the app itself is kind of fancy, so people signed up for fun and then just randomly guess the answers and try to check out how the app looks like. So we had to do some filtering, but after we filter the data, pre-process the data, these are the results. So the first 2 rows are corresponding to our algorithms, which have improved interpretability, but we don't know whether it actually achieves the state-of-the-art prediction performance. So if you look at the other rows, the first row, M2PR, actually is achieving slightly better prediction performance than our algorithm. But you can actually see that the gap is very marginal. So basically what it means is, by having those constraints, you somehow improve the interpretability, but you're not compromising the prediction result performance that much. And also you can compare with the other methods, something like MIRT and logistic regression and question-based visualization and so on. But the key thing is the first few methods that provide reasonable prediction performances, they are not scalable approaches. I mean, you can make them scalable, but as they are, it's not a scalable approach. So that's the reason why we want to have both scalable and interpretable results, as well as achieving the state-of-the-art performance. Okay, so let me just give you one interesting applications of our improved interpretability. So it's actually, it can be used for correcting tags. So in order to, before I explain how we can do that, let me first explain our data set and these tags. We actually have hired 15 experts to manually tag each of the 2,000 questions that we have. So they first gathered together and came up with 69 concepts to describe this 2,000 questions. And they tagged each of the questions with this concept. And this is the histogram that they came up with. If you look at the histogram, some of the concepts are devised and then they are used much more frequently than the others. And actually some of the concepts are not ever used, not even used for the entire question. So turns out that this kind of tagging approach using the human expert is not good, does not provide any insight, and also we try to exploit this information to improve the prediction performance, but we couldn't succeed, so that's another thing that we presented last year's NIPS workshop. But anyway, so this kind of human-based tagging could be useful, but it has lots of biases and errors. So the question is, how can you correct this tag information in a data-driven way? So this is the way that we propose. So let's consider two hidden concepts. So you draw the custom features on this 2D plane. The x-axis is the first element of the custom vector. Y-axis is the second element of the custom feature. Then you will see this many questions. One question you can ask is whether two closely located questions are annotated with the same tag. The answer is actually no. So the reason is because we have lots of different tags. We are trying to project everything down to the 2 dimensions, and it's hard to distinguish them from the 2-dimensional with the same tags. But the idea is the other way around. The key is if you look at the two questions that are annotated with the same tag, are they closely located in this 2-dimensional space? The answer is usually yes. So this is an experiment-based observation. But actually, the picture looks like this. So the red points are the questions that are tagged with the same tag. Greens are the ones annotated with the same tag, and so on. And actually, even though they have some overlaps, they usually co-locate together. Then the idea is, so if you look at this figure, then for instance, let's say this blue dot is tagged with the same tag with this question, but it's somehow far away from this cluster. And also this orange dot is also far away from this orange cluster, and so on. So if you can find those questions, you may be able to correct the tags. So that's the idea. So we went through our tag information, and this is the most interesting example. So there was a tag that was for oneself, by oneself, on one's own. So that's some random tag that the experts came up with. But there are 11 questions that are annotated with the same tag. So we projected on 1D, and these are the 11 points. It seems like there are 3 clusters. We looked at each of these clusters. The last cluster turns out to be a cluster that consists of wrongly tagged questions. It's very interesting observation. So if you look at these questions, for instance, question 9, if you look at the last part of the sentence, there's a phrase called the offensive logo on them. So maybe the expert was doing this very roughly, and then this was confused with on one's own, just marked it with this tag. Question 11 has a phrase which is a scenic view of its own. It's also very closely related to on one's own, so maybe they just randomly checked these tags. So we found this kind of wrongly tagged questions. And also for the other 2 clusters, it turns out that the first cluster was corresponding to on one's own itself, and the second cluster was corresponding to the first 2 phrases. So if you think about it, the first cluster requires some knowledge about the idiom. The second cluster may not require some specific knowledge about the idiom. It's just for or preposition plus oneself. So it turns out these 2 clusters can be separated by looking at this 1D projection of the feature vector. So it turns out the conclusion is we can help improve the tag quality by identifying wrongly tagged questions, or maybe you can identify new subgroups within the same tag and have a more delicate tag. Okay, so that's the conclusion, and thanks.